we present Reflect, a framework that summarizes robot experiences for failure explanation and correction. With the increasing demand for robots to work on complex tasks in diverse environments, failures are inevitable. However, it is tedious for humans to read through the long robot execution log and identify failures. It is thus essential for a robotic system to detect and explain its own failures automatically. We formalize the robot failure reasoning task into three main components. First, the agent needs to know what happened by summarizing its past experiences from raw sensory input data. Then, the agent needs to infer what went wrong by identifying and explaining the failure from the summary. And finally, the agent should plan what to do based on the failure explanation to correct the failure and complete the task. Recently, large language models have demonstrated strong reasoning and planning abilities, making it promising for robot failure reasoning and correction. The remaining challenge lies in how to generate an informative textual summary of robot experiences for LLMs to reason about. We observe two attributes of an informative robot experience summary. First, the summary needs to be hierarchical, with different levels of abstraction. The highest level should support general failure identification on either the execution or planning level, whereas the lower levels should support reasoning on failure details, such as the exact time and location of the failure event or the failure cause, all of which are useful for correction planning. Second, the summary should be multisensory. This is because certain environment details can be more easily identified through one type of sensory data than another. For example, it is easier to decide if water is running from faucet using auditory cues rather than visual ones. To achieve these goals, we propose a hierarchical multisensory robot summary for failure reasoning. At the base level, unstructured multisensory robot data are summarized into a structured and unified representation. Given RGBD observations, we first detect task-relevant objects in view, inferring object states using a visual language model like CLIP, and extract the object spatial relations using depth. These information are stored as a task-informed 3D scene graph, which can be easily converted into a textual caption of the frame. Similarly, the audio track can be summarized by running sound event classification with an audio language model such as AudioClip. To retain only information necessary for failure explanation, keyframes are selected when there are changes in the visual scene graph, an audio event, or a robot event, such as completion of a subgoal. The captions of the keyframes are concatenated to form the event-based summary. Finally, to support fast localization of failure, the subgoal-based summary consists of the end frame for each subgoal execution to reflect the general task progress. With the robot summary, we propose a progressive failure explanation algorithm to systematically query the large language model. The method will first iteratively prompt LLM to verify whether a robot subgoal is satisfied given the subgoal-based summary. Here's an example in the task salted carrot slice. Here, the LLM identified that the subgoal sliced carrot is not satisfied. If a subgoal is not satisfied, then the event-based summary up to the failed subgoal will be retrieved for further explanation. It is also possible that all subgoals are satisfied due to mistakes in the robot plan itself. Here's another example in the task boil water. In this case, the final failure state will be retrieved from the sensory input summary to infer mistakes in the robot plan. Finally, given the failure explanation, we can prompt LLM to generate a plan for the robot to correct the failure and complete the task. To ensure the generated plan is executable, we map each action in the plan to its closest executable action in the task environment using a sentence embedding model. To evaluate our approach, we create the robot fail dataset with a variety of tasks and failure scenarios in both simulation and real world. A distribution of the general failure categories is shown above. Here are some example tasks in the robot fail dataset. For the rest of the video, we'll show 2 demos of the summary and failure explanations generated by our method in real world. For more results, please check out our project website. Thank you. Here are 2 quick demos of the failure explanations generated by our method. On the left, we show a task when the robot goal is to secure knife and pear in their suitable containers, that is, knife in drawer and pear in fridge, but the original plan put them in wrong locations. With observations from the robot summary and embedded common sense knowledge, LLM is able to reason that the plan is incorrect. On the right, we show a task when the robot accidentally dropped the knife when approaching the carrot and the carrot ended up not sliced. With the multi-sensory robot summary, the exact failure event and time are identified.